Hello everyone, welcome to my channel Chemistry is Fun. Today we will deal with a new property, depression of freezing point. Now before we go to this topic, let us see what the freezing point is. Now the freezing point can be termed as the temperature of a liquid at which it changes its state from liquid to solid at atmospheric pressure. So the liquid is changing its state to solid and atmospheric pressure is maintained, then that temperature is the freezing point. So it can be stated as that temperature at which the vapor pressure of the liquid will be equal to vapor pressure of the corresponding solid, because liquid is changing its state to solid. So now this definition is on the basis of the vapor pressure. Now we know that whenever we add some non-volatile solute to the solvent, it lowers the vapor pressure of the solvent. So it will be in equilibrium with the solid phase at a lower pressure and hence at a lower temperature as well. This is caused because the solid and the solution, it will reach equilibrium at a lower temperature. So there will be a difference between the freezing points of the pure solvent and the solution. This is called as the depression of freezing point. So this difference between freezing points of the pure solvent and the solution, because we have made the solution by adding a non-volatile solute. So there will be a depression of the freezing point. So this depression of freezing point can be calculated by doing freezing point of solvent minus freezing point of the solution, because for the solution freezing point is less. So delta T will be equal to freezing point of the solvent minus freezing point of the solution. Now see, we can plot a graph between the vapor pressure and the temperature for a solvent and two solutions of different concentrations. So we term them as solvent solution 1 and solution 2. So one is a pure solvent and there are two solutions. Now here we see this is a curve CFB, you can see in this figure. CFB is a curve for a solid solvent. The solvent, this one, solution 1 and solution 2, their vapor pressure curves meet CFB curve at the points BFC. CFB curve at the points B for the solvent, F for solution 1 and C for solution 2. And correspondingly we find that T0 here, T0, T1 and T2 are for, these are for, you see this T0 is for the solvent, then solution 1, solution 2. So the temperatures T0, T1 and T2 for solvent, T0 is for the solvent, T1 is for solution 1 and T2 is for the solution 2. Their corresponding vapor pressures will be P0, you see P0 is for the solvent, P1 for solution 1, P2 for the solution 2. So this is the graph. Now if we have a very dilute solution, we find that the curves FD and CE are almost straight lines. FD and CE, FD, this is F, this is D, FD and C to E, these will be almost straight lines if the solution is very dilute. Curves FD and CE are almost straight lines. At the same time CB, C2B, you can see in this graph, CB also is a straight line. So we get two triangles BEC, this one BEC, and triangle BDF. BDF, these two triangles are similar. Now using the properties of similar triangles, we can say that EC by DF will be equal to BE by BD. So then what is EC? In the graph we see EC. E to C. EC will be equal to T0 minus T2. T0 minus T2. So we write T0 minus T2 here, divided by DF. In place of DF, what we can write? T0 minus T1 will be equal to BE. What is BE? You see B to E. That is P0 minus P2. B to E is P0 minus P2. So P0 minus P2 by P0 minus P1. So T0 minus T2 is delta T2 and T0 minus T1 is delta T1. So we get delta T2 by delta T1 equal to delta P2 by delta P1. That is the change in the vapor pressure. So from this equation we can state that delta T is directly proportional to delta P. That is, depression of freezing point delta T will be proportional to the lowering of the vapor pressure. Okay, so vapor pressure has also lowered. We know whenever we add a non-volatile solute, it will always lower the vapor pressure of the solvent. Now for very dilute solutions, we have already seen that Raoult's law states that P0 minus Ps by P0. Now what is P0? P0 is the vapor pressure of pure solvent. P0 minus Ps by P0. P0 is the vapor pressure of pure solvent and Ps is the vapor pressure of solution. So we already have this equation with us. P0 minus Ps by P0 equal to Wa by Ma into Mb by Wb. We can shift P0 to the other side, so we get this equation. P0 minus Ps equal to Wa by Ma into Mb by Wb into P0. This P0 is shifted to the right hand side. In my previous video, I have derived this equation. You can just go through that video. Now for a pure solvent, P0 and Mb is constant. So this P0 value, this P0 we can take as a constant, Mb is also a constant. So P0 minus Ps becomes directly proportional to the rest part, Wa by Ma into Wb. What is P0 minus Ps? That is delta P. That is directly proportional to Wa by Ma into Wb. From the above equation, we already know that delta P is directly proportional to delta T. So delta T also becomes proportional to this. So from here, in order to remove this proportionality sign, we have to multiply with a constant, that is K. So delta T is equal to K into Wa by Ma into Wb. K is a constant called the depression constant. Now in this equation, if you take Wa by Ma as 1, Wa by Ma is 1 and Wb is also 1 grams. Then from here delta T becomes equal to K. So if Wa by Ma is 1, okay, that is 1 mole we are taking, and Wb is 1 gram. 1 gram of solvent. So this Wb is 1 gram of solvent and Wa by Ma is 1, means we are taking 1 mole of the non-volatile solute. In this case delta T is equal to K. So from here we can define. So depression constant will be equal to the depression of freezing point, which will be produced when 1 mole of a non-volatile solute is dissolved in 1 gram of the solvent. But if you take Wb as 100 grams, if we increase Wb as 100 grams, we keep 1 mole only. Wa by Ma is equal to 1, but Wb is 100 grams. In this case, delta T is equal to K by 100. This new constant is called as K dash now. K dash is the molecular depression constant. K dash is the molecular depression constant. It is the depression of freezing point which will be produced when 1 mole of the solute is dissolved in 100 gram of the solvent. So now the relation between K and K dash is K equal to 100 into K dash. So here instead of K we can also write 100 K dash, because earlier we got the equation K into WA by MA into WB. So here in place of K we can put 100 K dash. So we get delta T is equal to 100 K dash into WA by MA into WB. If we further increase the value for WB up to 1000 gram and we keep the number of moles as 1 only, that is if WA by MA is 1, number of moles is 1 and WB is 1000 grams, then we get a new constant delta T is equal to K by 1000, that is Kf. This Kf is the molar depression constant and K is equal to 1000 Kf. K is 1000 Kf. So we can define this molar depression constant as the depression in freezing point which is produced when 1 mole of the solute is dissolved in 1000 gram of the solvent. Then we get this molar depression constant. So today we have seen the graph between vapor pressure and temperature, and also we have gone through the constants, molecular depression constant and also molar depression constant. I hope you all could understand the topic which I discussed today. Thanks for watching my video. Please subscribe to my channel. Thank you all.